Good morning, everyone. Welcome. So we're going to go ahead and get started in Chapter 6, Section 1. So in this section, there are a lot of definitions. So let's go ahead and get started. So the first thing we want to talk about is our definition of an angle. So given three non-collinear points, A, B, and C, we have the following. If we have the point A, the point B, and the point C, we would write it in terms of our symbol as the angle A, B, and C. We're going to have a revised definition of an angle a little bit later on, but that's the one from geometry we're going to use to get started. The next thing we want to talk about is an acute angle. An acute angle has measure greater than 0 degrees, but less than 90 degrees. So 0 is less than the acute angle measure, and 90 degrees is greater than. When we are talking about angles, it is customary to use Greek letters. So the most common one that we're going to use for an angle is the Greek letter theta. We have a couple of others. So we have phi, and we have alpha, and we have beta, and lastly, gamma. And there are plenty of other Greek letters, but it's pretty common to use Greek letters to represent angles. And among all of them, these are the most common symbols. For angles, our next definition is of a right angle. A right angle has measure exactly 90 degrees. Building on that, we have a right triangle. A right triangle has exactly one right angle. In terms of a picture, that's a terrible picture. Let's try again. We have our right triangle. We make this little box thing, and that represents the right angle. And then our right triangle is going to have two legs, which we label A and B. So these are legs. And it doesn't matter which one's A and which one's B. And then finally, we have the hypotenuse, which we are going to represent with the symbol C. So let's write down some facts about this. The side C aka the hypotenuse, is always the longest side. The lengths of A, B, and C are used to define the trigonometric ratios. The trigonometric ratios are functions with domain the set of all angles and range the set of all sides of ratios of right triangles. Alright, so let's think on this for a second. So, trigonometric ratios are functions where we input an angle and our output is the ratio of the sides of a right triangle. Alright, so there are two special triangles that we're going to need, and in order to help us with our definitions here, we're going to take a look at these triangles. So the first one is if we have a right triangle that looks like this, we can define all of our trigonometric ratios in terms of that triangle. And there are two special triangles down here at the bottom that are going to help us calculate the values some of these things. Alright, so we have our two triangles here. Both of these are right triangles containing only the right angle and then two acute angles. And then we have our following definition. So let's take a look at the definitions of our trigonometric functions right here. So by definition, we're going to have these 6 trigonometric functions. The sine of theta, whose symbol is sin theta, by definition is the opposite side of the triangle across from theta and the hypotenuse. Similarly, cosine theta is going to be adjacent divided by hypotenuse. Tangent theta is opposite over adjacent. Cosecant theta, notice in its symbol we have cosecant theta, but it is the reciprocal of the sine function. So we're going to have cosecant theta is 1 over sine, and the reciprocal of sine, so sine was opposite over hypotenuse. If we take that reciprocal, we get hypotenuse over opposite. We get a similar relationship between secant and cosine, and cotangent and tangent. So one of the reasons that relationship is going to be important is if we look at our graphing calculator, we'll see that we have sine, cosine, and tangent right here on our graphing device. Every scientific calculator will have those 3 trigonometric functions. Most of them won't have cosecant, they won't have secant, and they won't have cotangent. We'll have to use the fact that if we need those, it's 1 over one of the trigonometric functions that we know. So keep that in mind when it comes back to the calculator, and we'll mention that again a little bit later. Alright, so we're now equipped to take a look at our first example. So for example, if I were to ask you to find the sine of 30 degrees, the cosine of 30 degrees, and the tangent of 30 degrees, we could go and look at our sheet. So we know sine is going to be the opposite of theta over the hypotenuse. We have our 2 special triangles. So our 2 special triangles are the 30, 60, 90 right triangle, which has side lengths 1, square root of 3, and 2. And then we also have our 1, 1, square root of 2 right triangle, which has the 2 angles of 45 degrees. So when we want to figure out the sine of 30 degrees, we have our 30 degrees here. So we get this angle right here in that special triangle. And sine, by definition, was opposite of theta over hypotenuse. So we have opposite over hypotenuse. So then the sine of 30 degrees, well, the opposite side is going to be 1, and the hypotenuse, as the side across from the right angle, is going to be 2. So we get the sine of 30 degrees is going to be 1 divided by 2, which gives us 1/2. Similarly, if we look at cosine, the cosine is adjacent over hypotenuse. So in our diagram up here, the adjacent side to 30 degrees is going to be square root of 3 over the hypotenuse. Sorry, wrong color there. Square root of 3 is blue. Over the hypotenuse, which is still 2. So we get the cosine of 30 degrees is root 3 over 2. And this is the exact answer. And if we grab our graphing device, we can ask it, well, what is the cosine of 30 degrees? And our calculator gives us this as a decimal approximation. But if I were to check that by going the square root of 3 over 2, I press enter, and we'll notice I don't get the same thing. This has to do with something we're going to talk a lot about in this class later, but if your calculator's giving you this answer when you type in cosine 30 degrees, the 0.15, that means our calculator's in radian mode, and we need to switch it to degree mode. So let's go up on our calculator and hit our mode key, and the third choice down from the top, you'll notice radian is highlighted. We need to change it from radians to degrees. We're going to go ahead, after selecting that, quit back to our home screen, and this time, when I press enter on my calculator, I get this value, which is the correct value. And notice that it is equal to the square root of 3 over 2. So it's worth noting, and I'm just going to write it down here, if you get this value, cosine of 30 equals to this, your calculator is in the wrong mode. So you have to press your mode key like we just did a second ago and turn your calculator from radians into degrees. All right, we had one more thing in this problem, which was we wanted to calculate the tangent of 30 degrees. And tangent is opposite over adjacent. So that's going to be opposite of 30 degrees over adjacent to 30 degrees. So we get the tangent of 30 degrees is going to be opposite over adjacent, so 1 over the square root of 3. And that is a form of the correct answer, but it needs to be simplified. So we're going to rationalize the denominator. By multiplying the top and the bottom by the square root of 3. And when we do that, we end up with 1 times the square root of 3 is the square root of 3. Square root of 3 times the square root of 3 is 3. And that's going to give us our exact value. And once again, if we wanted to double check that, we could say, well, what's the tangent of 30 degrees? And if I go square root of 3 and then divide that by 3, I get the same value. Alright, here's a U-try for you guys. If the sine of theta is equal to 12 over 13, and cosine theta is equal to 5 over 13, find tangent theta, cosecant theta, and secant theta. So we start by drawing a triangle. There is my right angle, and I'm going to call this theta. We don't really know where theta is, and it doesn't matter if you put theta up here. As long as you keep everything located in the right place, we're not going to have any problems. So now sine theta, remember sine theta by definition is opposite over hypotenuse. So this is going to be my opposite, and this is going to be my hypotenuse. So the opposite of theta is over here, and we know it's going to be 12, and the hypotenuse has to be 13. Similarly, with cosine, we know it's adjacent over hypotenuse. So then the adjacent to theta right here has to be 5. So then this gives us a 5, 12, 13 right triangle. And we can answer each of these. So now if we need to find the tangent of theta is opposite over adjacent. That's going to be 12 over 5. And then we have cosecant of theta. And cosecant is 1 over the sine. And sine was opposite over hypotenuse, so it's going to be hypotenuse over opposite. And notice that 13 over 12 is the reciprocal of 12 over 13, and we're going to get the same thing for secant, and it's related to cosine in the same way, so we're going to end up with 13 over 5. So there is a relationship between tangent and sine and cosine, and that is the following theorem. We have that the tangent of theta is equal to sine theta divided by cosine theta. And this comes from the fact that if we go to the definition of sine theta, so sine theta, by definition, is opposite over hypotenuse divided by cosine, which is adjacent over hypotenuse. And if we have a fraction divided by a fraction, we multiply by the reciprocal of the denominator. And we notice that when that happens, hypotenuse and hypotenuse reduce out, and this all reduces to opposite over adjacent. Well, that is, by definition, the tangent of theta. So this proves that sine divided by cosine is the same as tangent theta. All right, the next thing we want to talk about are similar triangles. So our symbol for similar triangles is, we have our triangle ABC, and then similar is this wavy thing to triangle DEF. The symbol is read as the following. Triangle ABC, and this symbol is similar. And we have the following properties about similar triangles. So two triangles are similar if one, all angles are equal, That's our angle, angle, angle case. And the next one is the ratios of their corresponding sides. Are equal. So in terms of a picture, if we have the triangle ABC and another triangle DEF, we would then have the following, that the ratio of the side AC divided by DF would be the same as AB divided by DE, which would also be equal to BC all over EF. So, for example, if we had the right triangle, the side lengths 3, 4, 5, and then we had another triangle with side lengths 6, 8, and 10, if we were to calculate the sine of theta in each of these triangles, we would get the following. So in the small triangle, sine theta would be opposite over hypotenuse, which is going to be 4 over 5. And in the large triangle, the sine of theta would be opposite over hypotenuse again, which would be 8 over 10. The 8 over 10 reduces to 4 over 5, and we have the same value. And it's worth noting that this will always happen, that similar triangles will always have the same trigonometric ratios. So why is it that similar triangles would always have the same trigonometric ratios? Well, according to this, it says the sides are proportional. If we look at our concrete example, what is our scale factor or our constant of proportionality for the sides of the triangle? Well, here we have a 3 and it corresponds to the side 6. We have 4 corresponds to 8 and 5 corresponds to 10. In this example, we can see that the sides of the second triangle are twice as big as the sides of the first triangle. Well, that's our proportionality constant then, is 2, because what this is saying is if I take the side 10 and divide it by 5, I get 2. If I take the side 8 and divide it by 4, I get 2. If I take the side 6 and divide it by 3, I get 2. The reason that's going to happen is if we form the trigonometric ratios, we get 8/5, but 8 and 10 each contain that scale factor of 2, and it reduces out to give us this. So we get the same fractions because they always reduce to the same value because we're scaling the triangle by the same number in both the numerator and denominator of the fraction. All right, let's take a look at our next example. So if tan theta equals 1/5 and theta is an acute angle, we want to find sine theta and cosine theta. So we know that tangent theta is equal to 1/5. So let's just draw some triangle. Here's our right angle. I'm going to call this theta. Then by definition, we know that tangent is opposite over adjacent. So I'm going to get opposite is 1, and my adjacent is going to be 5. So that gives me two sides of the triangle. To find the missing side, we're going to use the Pythagorean Theorem. And the Pythagorean Theorem tells us that a squared plus b squared equals c squared. So in this case, we have our two legs, so we have 1 squared plus 5 squared equals c squared, which gives us 1 plus 25 equals c squared. So 26 equals c squared. Taking the square root, c is equal to 26, or the square root of 26. So now that we have our hypotenuse, we can find sine and cosine. So the sine of theta is going to be opposite over hypotenuse, so 1 over the square root of 26. And then, as we saw earlier, we can't leave a radical in the denominator, so we will rationalize by multiplying the top and the bottom by the square root of 26, which gives us the square root of 26 over 26. And we do the same thing for cosine. Cosine is going to be adjacent over hypotenuse. So we get 5 over the square root of 26, and once again, rationalizing the denominator, we multiply the top and the bottom by the square root of 26, and that gives 5 square roots of 26 all over 26. Alright, let's take a look at our next example. A scout group wants to estimate the height of a tree. They measure the distance a distance of 20 feet from the base of the tree and estimate the angle to the top of the tree to be 60 degrees. How tall is the tree? All right, well, let's draw a picture. We've got some tree, looks like this. And we've got our stick people over here. And we know that the measured distance from the base of the tree to the person is 20 feet. We also estimated that the distance, or the angle, to the top of the tree was 60 degrees. And what we are trying to find is this distance here, which is going to be the height of the tree. So if we look at this angle that we have here, we have our angle, and we want the height, and we want the adjacent side. So which trigonometric function is going to tell us about this? Well, if I were to draw just a small triangle, to make this a little bit simpler, I have 60 degrees. I have h, which I don't know, and 20. So then I would know opposite, and I want opposite, and I know hypotenuse. So opposite over, or I know opposite and adjacent. So opposite and adjacent give us tangent. So that would tell us that the tangent of 60 degrees is equal to the opposite side divided by the adjacent. So solving for h in that equation, we get h is equal to 20 times the tangent of 60 degrees. And if we go back and look at our special triangle, for 60 degrees, we have 60 degrees here, so tangent is opposite over adjacent, so that's root 3 over 1, so we're going to get the square root of 3. So the exact answer is 20 times the square root of 3. And if we grab our calculator, we would have 20 times the square root of 3 gives us this. Or if we just put that into our calculator, we have 20 times the tangent of 60 degrees, and we get the same value. So we would approximate that the tree is probably about 35 feet tall. So the situation that happened in that previous example comes up quite a bit. And what I mean by that is the angle. So what we had is the horizontal, and then we had this measure of an angle from here to here. So we had the scout group looking up at the top of the tree. So this angle, let's go ahead and call it alpha, and since these two horizontal lines are parallel, this represents a transversal. So by opposite interior angles, we know that that also has to be the same angle. Each of these are given a special name. So the angle, when we are looking up from the horizontal, is called the angle of elevation. And the angle, when we are looking down from the horizontal, is called the angle of depression. And those will always be positive angles. They'll always be equal. So if you hear the angle of elevation, that means we're looking up from the horizontal. And if you hear the angle of depression, that means we are looking down from the horizontal. All right. So historically, angles were measured in degrees, minutes, and seconds. The relationship was the following. 1 degree is equal to 60 minutes. One minute was equal to 60 seconds. Combining these two, then that would give us that 1 degree was equal to 3,600 seconds. And solving each of these, we get the following relationships then, that 1 minute is equal to 1/60th of a degree. Similarly, we would have that 1 second is equal to 1/60th of a minute. And our last one would be that 1 second is equal to 1/3600th of a degree. So historically, this is how degrees were measured. So our notation is going to look something like this. We're going to have degrees, minutes get 1 hash mark, and seconds get 2 hash marks. So for instance, if I wrote 3 degrees, 12 minutes, and 17 seconds. So this is read as 3 degrees, 12 minutes, and 17 seconds. So 3 degrees, 12 minutes, and 17 seconds. And I had a typo there. It had to have 2, just like over here. So 3 degrees, 12 minutes, and 17 seconds. All right, so let's go ahead and do some examples. So let's convert 6 degrees, 41 minutes, and 58 seconds into decimal degrees. So, using our conversion factors that we had above, we have our 6 degrees plus 41 minutes. Well, 41 minutes in terms of seconds is 1 minute is 1/60th of a second, so plus 41 over 60, plus our last one is 1 second is 1/3600th of a degree, so 58 over 3,600. And if we add all of that up on our calculator, we get 6 plus 41 over 60 plus 58 over 3,600. We get this, and then we're going to press math, and we don't do this very often, but we want a decimal because it asked for decimal degrees, and that is going to be our solution in degrees. So 6.6994 repeating degrees. So it's worth noting that our calculator can do pretty much all of this. So what we'll notice right here is that we have a secondary function right here that says angle. So let's go ahead and try to type 6 degrees, 41 minutes, and 58 seconds into our calculator. So I go 6, and then I press my angle. So I go second and apps to get my angle. And we'll notice the very first thing is degrees. 41 minutes, so I go 41 back into my angle menu. And choice number 2 gives me minutes. And then I need 58 seconds. And I go back into my angle menu. And I notice something is missing. I have degrees, I have minutes, and then my next thing I have is an R. We'll talk about that guy later. And then I have DMS, which looks kind of like our frac. We're going to come back to that guy in a second too. But we'll notice seconds is missing. For whatever reason, let's quit out of this. So second quit, go back to the end here. Texas Instruments forgot to put seconds inside that menu. The seconds are located over here as the alpha function on our plus key. I know, weird. So we go alpha and plus, and now we have our 6 degrees, 41 minutes, and 58 seconds. And when I press enter, it gives me the exact same value. So we can have our calculator do that. One thing that is worth mentioning is just like what we did earlier when we converted this fraction into a decimal, more often we've been converting decimals back into fractions, right? So we would go math and then frac, and we get this, and we're like, yay! And then I can turn it back into a decimal. Something you may have noticed under your angle menus, if you go second angle, I have a similar function that says DMS. And what that means is convert this angle as a decimal into degrees, minutes, and seconds. And when I press enter, it gives me back 6 degrees, 41 minutes, and 58 seconds. All right. So last U try for you guys. So let's have your U try be find the cosine of 84 degrees, 10 minutes, and 39 seconds. So this one's going to be calculator food, so we pull out our calculator. We go cosine 84, and we've got to go alpha angle to get our degrees, 10 minutes, so alpha angle, we grab our minutes, 39 seconds, and remember, it's not in the angles menu. We press alpha plus to get our last one, we press enter, and that gives us our cosine of 84 degrees, 10 minutes, and 39 seconds. All right. Last example for this section is we want to find an acute angle theta such that the tangent of theta is equal to 2.032. So to do this, we're going to use our graphing calculator. So we're going to call tangent theta y1, and we're going to call 2.032 y2. We grab our calculator, we put our y equals in, and we're going to go tan x and then 2.032, and then we're going to have to change our window. So we're looking for an acute angle, and we know acute angles are between 0 and 90 degrees. Nope, not 90. And let's change our x scale to 5, and we're looking for the value of 2.032. So let's go ahead and change this y min to 0, y max to 5, and then let's scale in 0.5s and go ahead and press graph. Alright, so we get these two things, and we're looking for the intersection, so we go second, calculate, intersect, enter, enter, enter. Our calculator thinks for a second and comes up with our angle, or our approximate point of intersection, is going to be 63.797. So theta is about 63.8 degrees.